In the previous video, we took a look at Mars, and I asked the question, how can you take a photograph of White Sands, New Mexico, and it looks exactly like a spherical planet such as Mars? I also took a look at a perfectly flat surface, in this case, the ceiling of my house, and we asked the question, why is it that when you view a flat surface through a prism, it takes on a curvature which looks almost the same as the curvature of Earth from space? And although the ceiling of my house and prism seems like a rather boring topic, let's follow the rabbit hole and see just where the answers to these questions will lead us. First, it's important to study how human and camera lenses produce their image. Let's peer into the workings of the eye. The reflected light of the world enters through the crystal transparency of the cornea, aqueous humor, lens, and vitreous humor to project onto the photoreceptors of the retina, whose impulses converge on the optic nerve and are sent to the brain to be transfigured into an image. Continual adjustments to the pupil and lenses regulate the entry and focusing of light. Here are a few observations to consider concerning the human eyeball. The human eyeball is a light-reading device that can only form an image if light can reach and enter the pupil. The human eyeball is a sphere and the pupil is a perfect circle. Light waves entering the cornea may only enter with the shape of a circle. Anything below the horizon, which is visible, takes its true form and shape, but when something is too far away, it becomes a dot or a circle and disappears into what is known as the vanishing point. Everything that is above the horizon, the sun, the moon, stars, and planets, are all perfect circles, and they're also very far away. In fact, if they were on the surface of the earth, they would be so far away that they would have disappeared into a circle known as the vanishing point. Are you positive that you're seeing the true nature of the celestial objects in the sky? Or is there some illusion from your fallacious light-reading eyeball? Because human and camera lenses are light-reading devices, we must consider the path which light has traveled before it reached our cornea to produce the image that we see. The refraction of light can create many different interesting optical illusions. Suppose we change the shape of the lens. Let's now return to our original shape. Suppose we change the location of the objects. The image can be either right side up, or it can be inverted upside down. A beam of light is composed of particles called photons. Photons are very different from the particles that matter is made out of. The image which you can see is developed from light photons, and it is not an exact translation of the physical matter around you. The speed of light through a vacuum is the same for all observers. But light slows down when it tries to pass through certain materials such as glass, water, and air. The velocity of light decreases with increased density of the material it's traveling through. When a wave enters or exits a material at an angle, the left side and the right side of the wave will cross the boundary at different times. The greater the angle, the greater the difference in time when the left side and the right side of the wave will change their speed. This causes the wave as a whole to change direction both when it enters and when it exits the material. This can be observed with the prism. Light traveling straight through the prism will continue in a straight line. If light enters the prism at an angle, the light will bend. The angle that light is traveling in relation to the media is called the angle of incidence. The greater the angle, the greater the bend. The refractive index of a medium is a number to specify how fast light will travel through it. For example, the refractive index of water is 1.333, meaning that light travels 1.333 times faster in a vacuum than in water. When light waves enter a medium such as water, prism, or air, it will bend. The refractive index determines how much the path of light is bent when entering the material. The greater the refractive index, the greater the bend. So there are two factors which influence how much light will bend when traveling through a transparent media: the angle of incidence and also the refractive index of the media. The total amount that light bends is called the angle of refraction. The atmosphere and air also refract light, just like water and a prism and a glass does. Light waves do not travel at the speed of light within the atmosphere, but light's velocity is continuously getting slower as light travels towards Earth through air which is continuously becoming more and more dense. A visualization of atmospheric pressure will help demonstrate this, as we know that air closer to Earth's surface is more dense than the air at the top of the atmosphere. So air high in the atmosphere, perhaps up in the exosphere, has a refractive index close to 1. But air near the surface of Earth has a much greater refractive index. This continuously changing refractive index causes light waves to follow a continuously curving path, as we know that light follows a curved path in a medium in which the refractive index changes. This is a study of the physics of the air and atmospheric refraction, which consists of three phenomena: astronomical refraction, terrestrial refraction, and a third and yet unaccounted for, horizontal refraction. Let's look at each one in detail. First, we'll consider a viewer on the surface of the Earth who's looking up into the sky at a celestial object, any star or planet, typically the sun. Because light must pass through the atmosphere and is continuously bent, astronomical objects appear higher in the sky than they are in reality. This is called astronomical refraction. When navigating at sea with only a chronometer and sextant, you can determine an accurate longitude and latitude by taking a sighting exactly at noon when the sun is directly overhead. The only time there is no visual distortion is when the sun is directly overhead at high noon, or your zenith. When the sun is at your zenith, the angle of incidence is 0 degrees, and that's why there's no visual distortion. The light from the sun is entering the atmosphere at an exact 90-degree angle to the atmosphere's normal plane. As the sun moves away from your zenith, the angle of incidence is increasing, and thus the amount that light bends will also increase. You can replicate the effect of astronomical refraction by looking at a specific marker on the ceiling, and view the same marker by looking through the bottom of a prism. If you cover one eye with the prism and one eye without, you will notice the marker is visible in two different locations. The research papers included in this video explain how to calculate astronomical refraction. Here we've done the math on paper by hand. Please study our work for correctness and accuracy and provide any feedback. The paper is included in the research documents and the links in the description. Next, we'll consider a viewer on the surface of the Earth who's looking into the distance at a terrestrial object, such as mountains in the distance or the visible horizon line. Another good example of this is when you're looking at a ship at sea and it's disappearing into the distance. The curving of light rays is not confined to those that come from some celestial object, but also applies to those that pass between any 2 points within the atmosphere. This phenomenon, known as terrestrial refraction, causes all objects on Earth or in the atmosphere to appear to be at greater altitudes than they actually are. Even initially, horizontal rays normally curve down towards the surface of the Earth so that objects at the observer's own level, as well as those above or below it, appear elevated. To understand this phenomena, consider a light wave normal to the surface of the Earth and consequently moving horizontally. If now the density of air decreases with increased elevation, as it nearly always does, the upper portion of the wavefront will bend down towards the Earth faster than the lower, and the path will be bent down towards the Earth along a curve whose radius depends upon the rate of this density decrease. In this video from Skunk Bay, it's easy to see the effect of terrestrial refraction. Consider what this looks like from the side. A curve with a radius that's constantly changing. Notice how terrestrial refraction is responsible for a visible curvature on the horizon line, regardless if the Earth is a sphere or flat. As a common approximation, terrestrial refraction is considered as a constant bending of a ray of light, or line of sight, in which the ray can be considered and described as a circular path. Once again, we've included the research papers which explain how to calculate terrestrial refraction. Please study our work for correctness and accuracy, and provide any feedback in the comment section below. For every action, there is an equal and opposite reaction. Considering there is strong visual distortion for the viewer on the surface of the Earth who's looking out through the atmosphere, and complicated mathematics are required to correct the distortion, what math formulas are then used to correct the visual distortion for the viewer who is outside of the atmosphere and looking back down to Earth? Wikipedia does not discuss this phenomena. Astronomical and terrestrial refraction are both instances where the viewer is on the surface of the Earth. Physicists do not discuss the phenomena. It's as if they assume that there's absolutely no visual distortion for the viewer outside of the atmosphere, which is a complete physics fallacy. Now, every time you've heard someone say, "The Earth is a sphere, haven't you seen pictures from space or from the ISS?" you can be sure they're assuming there is absolutely no visual distortion for the viewer in space. They certainly have never considered that mathematical formula must be applied to fix the distortion in the image they're referring to. So I'll ask you, the viewer, a question. Given astronomical and terrestrial refraction, what is the mathematical formula to correct visual distortion for the viewer who is outside of the atmosphere and looking back down to Earth? What effect does this have on the horizon line? If you have a serious answer, please comment below. Our research has led to a single truth. The horizon of Earth, when viewed from space, will suffer from visual distortion. The actual horizon and the apparent or visible horizon are not the same. Mathematical formula must be used to correct the distortion caused by the atmosphere so we know the true shape of the horizon line. Remember, there are two factors which influence how much light will bend when traveling through a transparent media. One, the angle of incidence, and two, the refractive index of the media. What is the angle of incidence for the viewer in space looking down to Earth? Their zenith, or high noon, the point where there is no visual distortion, exists directly in front of them. As you deviate away from this point, the angle of incidence is increasing. The same effect can be seen with astronomical refraction. At the viewer's true zenith, or high noon, there is no visual distortion. But the greater you deviate away from this point, the greater the distortion. And once again, you will find the point in the middle of the horizon to be the zenith, and as you deviate away from this point, the angle of incidence is increasing, and thus the image and horizon line is being distorted from its true location and altitude. Here's a diagram to explain angle of incidence. The normal is your zenith. When on Earth, this is the point in the sky directly above the observer, and when you're outside of the atmosphere looking back down to Earth, this is the point directly in front of the observer, the middle of their view. In astronomical refraction, the further a celestial object is located away from your zenith, the more its apparent altitude becomes distorted from its true location. Likewise, in horizontal refraction, the further a point on the horizon is located from your zenith, the more its apparent altitude becomes distorted from its true location. The visual distortion caused by the atmosphere causes the horizon to form a curve, with a specific radius of curvature determined by variables such as the viewer's altitude and the angle of the lens. Here, a 3D simulation shows the effect. A camera icon represents a human or camera lens. The math used for this simulation is included in the documents and is derived directly from the known data concerning atmospheric refraction. The higher up you are in the atmosphere, light must travel through more layers of atmosphere to reach your lens, and thus it will be refracted at a greater amount. This explains why altitude affects the horizon's apparent curvature. You can replicate the effect of horizontal refraction by looking at a perfectly flat line through a prism. I know this line on my ceiling is perfectly flat. However, when viewed through a prism, it takes the same exact shape as Earth from space. Why? Again, its angle of incidence. The light traveling through the prism directly in front of me is not distorted. It travels through in a straight line. But when a wave enters the prism at an angle, to the left or the right side, the wave will cross the boundary of the prism at different times. The greater the angle, the greater the difference in time when the left and the right side of the wave will change their speed. This causes the wave as a whole to change direction both when it enters the prism and when it exits. The further away you are from your zenith, the more the light is bent, and the more the apparent altitude of the ceiling is distorted. To use a 1-inch prism which has a high refractive index, or hundreds of miles of Earth's atmosphere which has a low refractive index, is synonymous. In both cases, the same exact visual distortion will be seen due to light refraction and angle of incidence. To the aviator who has been to 80,000 or 100,000 feet and says, "I've seen the curve," I absolutely believe you. Did you notice how the curvature changes with altitude and angle? Or did you spend most of the time looking down towards Earth and thus seeing a downturned edge?
And from this height, 67,500 feet, the edge of our planet has a definitive curve to it. It is more three-dimensional than I have ever seen it. There we are.
Did you subconsciously ignore the optical illusion you were seeing, which is caused by light bending, and just accept it at face value? The Earth is a sphere, because you went up and seen it? I doubt these questions have been seriously contemplated, even by NASA personnel. The commentary as put forth by NASA is that Earth's visible curvature, as seen from space, is the actual curvature of the Earth, thus proving that the Earth is a sphere. And if you can see the curve, then you will know that the Earth is a sphere.
So tell me, Neil, is the Earth flat?
We have video from space of the rotating spherical Earth. The Earth is round.
Thank you for joining us on this episode.
Well, no, BOB's on the gram talking a lot of this stuff, and he's actually, he's got a GoFundMe. He's trying to buy a satellite to take his own pictures to prove.
So before you do that, why don't you consider joining the Planetary Society? We will have a satellite. Join the Planetary Society. We will have cameras that will take a picture of the Earth, and you can decide for yourself. Not a conspiracy. Come to Cape Canaveral and see the rocket launch.
After all, you can just go to Cape Canaveral and watch a rocket launch and you should be instantly convinced that the Earth is a sphere. Now, both of these men have assumed that there is no visual distortion for the viewer outside of the atmosphere who's looking back down to Earth. Most flat Earth theorists will say that every photo and video from space is taken with the fisheye lens and that the barrel distortion of the fisheye lens creates the curvature seen. This assumption means that the curvature is only seen in photos and videos, but would not be seen with the naked human eye. Additionally, this assumes that if a regular camera without a fisheye lens was used in space, that you would see a perfectly flat horizon. So we can see that Neil deGrasse Tyson, Bill Nye, and most flat Earth theorists all agree that there is no visual distortion for the viewer who's outside of the atmosphere, who's looking back down to Earth. And what about these two planets? This one, Mars. And this one, well, this is New Mexico. And since it's a circle in the sky, it must be a spherical planet, and that means Arizona is on the other side of the sphere. So how did New Mexico turn into a planet? Take a glass dome. No, not that one. There we go. Now go up to 24 miles elevation with Felix and look down to Earth.
Release the helmet tie-down strap.
Release the tree. What I can see. Sometimes you have to get up really high.
Ah, well, that's just a reflection in his dome-shaped helmet. But what does it show? Felix can see around him a perfect circle. Even when you're on the ground, you see a perfect circle. The horizon which surrounds you is always a perfect circle. You can't see the blackness of the stratosphere because you're too low, but if you go to 24 miles elevation with Felix, you can now see the blackness around you, and you can also see your visible circle beneath you. Keep going up, and that circle will get smaller and smaller. Keep going, and now you can't distinguish that circle from the moon or the other circles around you we call planets. And all of those other circles are spherical bodies, right? But the small circle you came from, that circle of New Mexico, is that really a sphere? Or is it a flat desert which you're just too far away to see? In summary, our research proves that visual distortion will be experienced for the human or camera lens outside of the atmosphere. When studying atmospheric refraction, you should not only consider astronomical and terrestrial refraction, but also the third and unaccounted for scenario, horizontal refraction, for when the viewer is outside of the atmosphere and looking back down to Earth's horizon. Our theory postulates the Earth's surface is perfectly flat and that the curvature seen from space is due to horizontal refraction. Likewise, when a viewer is on the surface of the Earth, the curvature is seen due to terrestrial refraction. And what about the movements of the stars and planets? Are they really moving, or is it just another optical illusion caused by the movements of light waves from a single light source? Given that light must travel on a circular path in order to reach your spherical eyeball, only to enter through a circular-shaped pupil, it's not surprising to see a plethora of circular-shaped objects that we assume are spheres in the sky above us. If you have any questions or comments about this topic, please type or ask in the comments below. The documentation and research papers can be downloaded from the link in the description. You are allowed to download, share, repost, upload this video, and use it in any way you want to. And there is an exciting new video coming soon, so subscribe if you don't want to miss any of the madness. Thanks for watching.